lacto pickles are there, no, from cucumber jerkin pickles. So the material is jerkin. Second one is the quantity of the lactobacillus. The lactobacillus we applied, and then how much of the time is fermentation time. Probably you can also put the salt concentration. So these four attributes we are putting it in the jerkin. Actually, jerkin is a material, but you are changing only three values: salt concentration, lactobacillus concentration, and the fermentation time. So there, everywhere there are 2 or 3 levels we take. So we take -1, 0, +1. So suppose if it is a lactobacillus microorganism concentration, in the 0 level, you have to do the survey, literature review. So wherever the jerkin pickle, the optimum level is identified, that will come under the 0. +1 and -1 you can put, suppose if it is some 220 cubical numbers. So we can say that 220. So we will put the 0, 200, 240, 200, 250, 240, 3 levels. Like that you can take it to 2 to 3 levels. Then you can generate the fractional factorial design, and then you can, I will also show you. The theory component is, it is basically used for optimizing the quality of the product which you are developing. Some food technology want to develop a jam. All the jam produced from the particular factory should have the same quality. Normally they define the quality based on either sensory attributes or the off flavor, like a shelf life to examine the shelf life, or else they use some proximate composition. Like you randomly take out a jam sample and estimate the total sugar content there, or maybe to estimate the anthocyanin content there. Then all sampled, that anthocyanin content means they might have already tested and put the value in the ideal sample. So it should match along with that. So this is the one which we are doing, and it is a statistical approach for optimizing the experiments, and it is developing a mathematical model how the factors, like I said, the incubation days, concentration of the lactobacillus as well as salt concentration, these three things together improve the sensory quality of the jerkin. Because that is a pickle. Means if you say pickle, the jerkin should have some kind of lactic acid content. Okay, one is lactic acid content of the jerkin, though the response variable will be lactic acid content in jerkin. That is a dependent variable. Independent variable means these three. And it helps to, this method helps to identify a set of experimental conditions which minimizes or maximizes the response value. Sometimes when you make a pickle, the lactic acid content, you will say that only certain level it is permissible, because otherwise it will be too sour. Because pickle should have optimum quality, the sourness is having some optimum quality. So up to this level only you can go for that fermentation. So you are, when you are going for, there are two things are there. First thing is you will generate the experimental design based on the levels of the different factors. Then you we give the experimental design to the food technologist. He will, on each experimental condition, he will generate the data of the lactobacillus content. Okay, then he will give us the data. You have to put the data there. You have to analyze it and to see that whether it is fitting into a quadratic model. Normally 2-3 models are there, like a linear model, quadratic model. Normally in the response surface we are looking for a fitting of the quadratic model. So the quadratic model is fit, and we will identify what are all the significant, I think you know about ANOVA, no? Basically an ANOVA table, which is the significant variables, 1, 2, 3, and the interactions as well as square. In quadratic model there will be ABC, then it will be like a AB, BC, AC, interaction component, then A square, B square, C square, and there will be constant. So you have to see that what all the different variables are having a significant value. And most importantly, in quadratic model, any interaction should be significant. AB, BC, AC. If interaction is not significant, we will not be able to get the quadratic model. Then once you are getting the significant values, then there will be a regression table. From there you have to take the coefficient, you have to fit the quadratic equation. You have to write down the quadratic equation. Once it is done, so you develop the model, then from there you have to identify the optimized conditions. So there is another procedure where you can go for the optimized condition. So it produces two graphs. One is a contour graph, second one is this 3D plot. So you have to make interpretation of this. I will show you one example how the data was interpreted and how it was written there. So before going into response surface methodology, there are in general experimental designs. So here you can see number of factors for the experimental design is 1, is a single comparison methods. If it is multiple, factors are 2 levels. Factors means they depend independent variables. It is a 2-level factorial design. It is whether it is possible to change, then yes, you can go for split plots. The agronomy people used to do this split plot. If there are not 2 factors, all factors are quantitative. I am telling levels means -1, 0, +1. These are 3 different levels of the factors. If all are quantitative, if there is no, then you can go for general factorial. Then if all factors are quantitative, the type based on the type of factor, you can go for the response surface methodology, or else if it is a mixture design. So this is a different kind of classification, because in social science we will have a different classification of experimental designs. True experimental designs, quasi-experimental designs, and other kinds. But this year, since we are looking at the product optimization, this is one of the area where different one classification which I am giving you. And this is the very common designs used in food product development. Fractional factorial design. This is not full factorial. Full factorial means if there is a 2 vectors, 2 levels means 2 square, 2 to the power 2. So you can see that many number of runs will come. So full factorial design, the problem is if you have more number of factors and more number of levels, the runs will be very high. So it is not possible to do the treatment, because when you are conducting every run, you will be conducting an experiment.
This phone belongs
every
to her.
run is an experiment. So if it is more than 24 runs, you have to prepare 24 experiments. So it is very expensive for food technology people. So that's why we don't. We go for a fractional factorial design. Taguchi design will help you to identify. So there are 7, 8 factors are there. Taguchi design will tell you which factor is more important than the others. So you don't have to put all the factors together. It is not an experimental design, it is a pre-experimental. It is used for the screening purpose. Normally we don't use the Taguchi designs. Engineers are using these Taguchi designs. And Pluckett-Berman design also, it will help you to screen the variables which are very important. Full factorial is actually the optimization, first level of optimization design. This central composites, box banking, these 2 are response surface designs. These 2 central composite designs and the box banking design. The central composite design is widely used in response surface methodology. But we don't use this because most of our paper we use box banking design, because it will give you less number of variables when compared to the central composite design. And optimal designs and mixture design, there are different kind of experimental designs which we use it in product development. So there are 2, I told about 2 different kind of designs. One is a screening designs and optimization designs. Screening, because optimization, what happens, you have to select 1 or 2 or 3 variables and different levels, and variables means factors, independent variables. Different levels of independent variable, you are trying to optimize the jam quality, that is a dependent variable. Okay. But here, when you don't know properly how many variables are required, I can give an example. One of the paper, like when I was collaborating, so he has told me that there is 3 factors. Like he told 3 levels. He has given us the levels. So I generated the response surface, that the experimental runner. We call it as runs. There will be maybe 1 to 24 runs. Each run means one full experiment. That will give you, this is the salt concentration, this is the incubation time, this is your lactobrevis concentration. So that fellow will take observations with this composition he write the value of lactic acid composition, then come to the second run, third run, fourth run, fifth run, sixth run, like that. But if you don't identify the zero level, -1, 0, +1, 3 levels, no? If you don't identify the zero properly, then there is a problem. One example, some people used to RPM, revolutions per minute. Okay, some people will say that the ideal RPM is 250. Okay, so then they say that okay, 250, I will put 150, this side 350. So you generated a design using 150, 250, 350. There are times where 150 RPM may not be there in that machine. So that will start from 200 RPM. So you generated a design for 150 RPM. So that means that you have selected a design which is not possible to use it. Okay. I will give you an example from technology. There is an example I will tell you about the psychology. So how they have done it, I will explain. So you have to identify the screening factors using the screening design. Fractional factorial, Pluckett-Berman design and Latin hypercube designs. This will help you to identify the suitable variables. So then once you are identifying the variables along with the levels, you can go for optimization. So identify the optimum values, you can use in refinement of the quality or optimization stages. It is a very high quality approach. So here you will be using central composite, box blanket, the optimal response surface and mixer design. I will give you an example of box blanket design, how we have interpreted. So this is some summary of the screening designs, whatever we discussed earlier. No, the qualities of the, you have to choose the screening design. If number of factors are less than 3, you can use the FFD design, fraction factorial. If it is more than 9, you can use all the 3 designs. Even 4 to 6 also, you can use all the 3 or 4 designs. Factor level, if it is more than 3, you have to use only Taguchi design. You cannot use these 2 designs. These are some of the decision matrix for which design is the best. So this is the steps in using the RSM. First thing is you have to collect the data. Data means you have to select the factors as well as responses. Factors are the independent variables. Responses normally it may be 1 or 2 or 3 or 4. So I was telling one example of lactic acid content, but there may be other responses also. So we can do for 1 response, we can do for 2 response, we can do for multiple response. So that is possible. Then you apply the RSM, create model and estimate the model from the data. So direct way, apply the RSM, create the model, generate the data and estimate the actual. First you create a model, then only they will go for a data like a experiment. They once they get the treatments, they do the experiment in the lab level, collect response data, then they will give you the final table. From there you will be estimating the model. So in the model, if the residuals are normally distributed, if it is randomly distributed, because 99% when you are getting the data from experiment, if you run it, it will not fit into any model. 99% first time response surface quadratic, because now response surface normally the journals will accept only the quadratic model. But we have done one linear model also. There is one paper we have done for linear model. But 99% when you are doing first time, then the food technology will get a heart attack. Because doing 24 experiments for a period of, food technology experiments, it is very difficult. they must do the treatment, they have to wait for some day, they have to do some HPLC to estimate the lactic acid content or whatever. So after 21 month or so, if it is not fitting, he will be totally mad. Then what you have to do, I will tell you, you have to look at the residuals. Error table. If the residuals are not properly distributed, if there is a deviation, we will select the specific item. We will say that that is an outlier. So you can change the value or you can transform the data. There is a lot of transformations are there, like a log transformation, natural log transformation, inverse Charge transformation. square root transformation. There are several transformations are there. Based on the, you have to go for skewness kurtosis, whether it is positively skewed or negatively skewed. So, anybody has attended a class on data preparation? Is there anything? No. They actually, that is must. Because when you go for analysis, it is very important to check the data. So, maybe if possible, let me complete it. My laptop, if there is any old presentation, I will show you how to do the data preparation. Because 4 things you have to see. First, you have to see outliers. Outliers can be identified using multiple methods, and one is a graphical method, where you can go for a graphical method. The outliers will be congregated below that. I will show you that how it is done. Then once you have a problem of outliers, you have to see that whether you will retake the outliers. Outliers are the response values which are significantly different from the average value. Okay, but what happened 99% times we will tend to delete the outliers. We should not do. Then there 10% trimmed mean method is there. 10% trimmed mean means that you just calculate the mean value. Okay, remove the outlier. Again calculate the 10% trimmed mean value. If there is no significant difference, you retake the outlier. If there is a significant difference, you have to remove the outlier. So everywhere you have to choose. The second data preparation is normality testing. You can go for normal probability plot, where all the in normal probability for I am telling everything you have to first variable wise response data. So if it is all the line, then you can say that this data is normal. If the data is non-normal, actually 5-point scale, when you go for Sangli, Agility, Sangli, Descending or any rating scale, 99% you will get non-normality unless you have a larger sample. If sample size is more than 300 or 400, you will not get a non-normal problem. Normal, you will get normality. But if it is less than 200, or maybe if it is less than 250 also, you will be getting non-normal. So, because otherwise you have to go for 7-point scale. 7-point scale, the distribution is uniform. So, to avoid the non-normality or to treat the non-normality, we have to go for skewness kurtosis. You just see. Some positively skewed item, there is a transformation method. Negatively skewed item, there is a transformation method. Leptokurtic, mesokurtic, there is a transformation method. So you can transform the data, the values of the particular variable, not the other variable. Then you can you will be getting. Otherwise, you have to transform into Z values, standard normal deviations. Because if your data is not proper, all issues will come. Model will not come, and there will be lots of issues. And I will give you one more example. When I am doing it, I will tell you what are the problems will come when you are doing further response surface methodology. If there is another concept called a lack of fit. Lack of fit, I will show you where the lack of fit comes. If the lack of fit comes into your model, it is nothing but the data is fitting into the quadratic model in general. Okay. That if the lack of it is not available, then you have to use the model graph to identify the interaction, then edit the model, and we have to redo the analysis. Then you will go to these two are problems. If you solve this problem, you will get the ANOVA value. So ANOVA, you can take the ANOVA, then you can go for analysis of the plots, contour plots as well as 3D plots. Then finally you will come to the answer. This is only up to ANOVA level. Then you have to go for optimization. That is the next level. There are numerical optimization methods are there, graphical optimization methods are there. Now even nowadays what we do, we go beyond RSM. In last 2 papers, whatever the optimal value you are getting in RSM, we validate using the ANN model, artificial neural network model. So that I am not showing, but that is normally very difficult, because fitting the ANN model itself, what you have to do is, you have to do first you have to run the algorithm. There are 3-4 algorithms are there. Then you have to identify the t value, and you have to create an error plot. Wherever the error is less, then those model you have to select. Because we will be training the model in ANN. So this is the description about the different RSM designs. Full factorial designs runs range from 2 to 21. It takes a two-factor interactions and the quadratic effects. It is efficient in estimating the value because it is a very effective model. This is a base model. In RSM, full factorial design is a base model, but the problem is it will generate so much of runs. Then runs mean experiments. 24, maybe around 28 based on the number of levels. So nobody can do 24 experiments or maybe 27 because people will get fed up in lab experiments. So otherwise that's why we go for the fractional factorial design is the Box-Bangkin method. But central composite design is widely applied in food science. If you take any paper, normally they go for central composite design, which is used when response variable is continuous. Response means your dependent variable. If it is not continuous, you cannot go for the central composite design. It is widely used for second, it is basically second order fitting, polynomial model. Box-Bangkin design is used when you want to have a smaller number of experiments. You don't want to spend because biological experiments are expensive because it takes chemicals, lot of chemicals and glasswares are used. So that's why people go for Box-Bangkin design. Taguchi design is using for selecting the most significant factors. And this is the steps in doing RSM. First, identify the problem and response variable, which is the factor, which is the response, and what is the problem you are trying to solve it. Then screen the potential factor variables. Normally, what happens in food technologies, they don't follow this. So this is very important. There are two ways you can do because you want to take some variables, you want to identify some levels, and you want to identify the quality of the particular pickle. Okay, but what the variable they are selecting, sometimes it may be irrelevant. Sometimes it is impossible variables. Because I told about RPM, no? Because machine has some limitations. Okay, for those things, you have to go for a proper literature review. So see the previous paper on pickles. What is the optimum value they have taken for incubation time or salt concentration or any other component. Then you select those things as 0. There will be -1, 0, +1. 3 different levels are there. So accordingly, otherwise you have to go for Taguchi design, select some of the run a mock experiment. Using the Taguchi design, you identify the most significant variables. Then you can do the coding and identify the factor levels. Then select the experimental design, what you want to do. Central composites or Box-Bangkin or D-optimal designs. Then you have to conduct the experiment and develop the response surface model. Check the model accuracy using the ANOVA R-square, because here you are selecting the quadratic model based on R-square value. So there are 2-3 R-squares. One is a model R-square, adjusted R-square, predicted R-square. Here the requirement is between the adjusted R-square and predicted R-square, it should not be more than 0.2. So then only you have to select the your best model. Then optimize the value and validate the model. And once you don't get a proper validation or optimized value, you have to iterate, means you have to go back to the first step 1. Check all the values. If you are not getting the proper values, why it is not coming, check the residual plots and check the other plots which are coming. I will show you when we are doing a mock exercise. Then from there you will be developing the model. Okay, one example in social science. Optimal color design for psychological counseling group. This is the room that they have done research for psychological counseling group. If somebody comes and sit in front of you and you are doing psychological counseling, maybe you can take a conversation or maybe a classroom. So they have used the response surface designs to optimize the color combination of a psychological counseling group. Because color is the very powerful aspect of the psychological counseling environment. Because people are coming inside the psychological counseling environment, they are sick. They are either declared sick or not knowing, or maybe through psychological diagnosis they will become that they have some problem. So sick means it is not mental. It is something like it starts from mind depression or maybe mind, even procrastination is also a psychiatric issue. Everybody has some level of procrastination. Laziness is also psychiatric issue if it goes beyond certain level. So when people are coming inside the clinic and psychiatrist or psychologist is sitting there, the room color. So they have done response surface methodology to optimize the color of the room in terms of their responses, the semantic differential scale. Whether it is pleasant, whether the room color is interesting, whether the color is exciting, whether the color is relaxing, safe or active. This is a semantic differential scale. They have taken each and every attribute one value. This is your response variable. There are 6 response variables here. Okay, but 75 patients and there are 2 experiments. Experiment number 1 42, experiment number 42. The color samples were stereoscopically projected. You can see L is one variable, black one. Here next you can see color, lightness and a different hue and saturation. So 4 different variables. You can see they have generated L, A, B. They have selected 3 variables. Here different levels. For L 3 levels are there. For A 3 levels are there. For B 3 levels are there. This is the generation you are doing. Up to this you will be generating. This is the response variable. So this is the response variable. These data you have collected based on the semantic differential scale. Okay. Here this combination, the light combination, they have taken 3 levels. 25, 50, 75. 3 levels of light they have taken and 3 levels of color they have taken. A and B are hue and saturation. 3 levels they have taken. So by combining the 3 levels, they have generated these colors. They have generated these colors. Here you can see 27 treatments, no? So 27 color cards are there. They did not use the color card. They have projected in the room. When the client is coming, no, that the colors are put in three dimensions. All 3 light where they put multiple projectors. The person, when the experiment is running, the person comes inside. He is seeing first one is this, second is this, third is this, fourth, fifth, sixth, up to 27. All the people will evaluate the 27 in the semantic differential scale. How much pleasant the treatment number 1, how much interesting the treatment number 1, how much exciting, how much relaxing, how much safe and how much active. So this is the values they generated. 1, 2, 3, 4, 5, 6. Okay, this data was generated through simply semantic. This is no experiment, simply semantic differential scale. They have taken the average value. Only the average value was put into the analysis. So now they got the model. You can see this is a significant model, ANOVA, and this is the quadratic equation they have generated. Here you can see mean CV. Here you can see adjusted R-square, predicted R-square, adequate vision. Here it is problem because adjusted R-square is 0.8, predicted R-square is 0.4. Ideally it should be less than, the difference should be less than 0.2. So this is clear, no? So you can try this kind of technique in your classrooms. Like a color of the classroom, whether it is affecting the effectiveness of the education or the students' color. But in my place, like because I am in charge of agribusiness incubator, if you come into my room, you will see that the back side is this color. In one room, in another room, we put this color. Complete. It is not paint, it is a wallpaper, plain wallpaper. So many people used to say that why you put this color. But when you are sitting in online meetings, it will give good color, bright background. You don't have to blur your background. And whenever you are taking any photograph inside our, and another room is green, this green. One is this, and another one is this. So that means that when you are coming inside, it should create some kind of feelings inside your mind. So I did not use this technique. Simply we wanted it to be different. Instead of putting a common color, we pasted this color wallpaper throughout the room. Studios you will see different different color of the wallpapers. When you go to studio with all letters and drawings, everything. Because when you are entering into your room, that will create a sense of attachment with the room which you are going. So this is the contour graph they have created. I will explain when the contour graph is there. This here the dimension you can see relaxing to distance. So this portion, this is the optimal point. This is the optimal point. And interesting, this is a 1, 2, 3, 4, 5. Actually there are 6 numbers, no, only 4 I have given. Each and everything there is a contour graph. Contour graph and the 3D graph will come only when there is an interaction. Here in the model, it is not a full table, it is only half table. But this is the interaction component. 1, 2, 3. Yeah, this is an interaction component. So interaction, any one interaction, AB, BC, AC, any one should be significant in quadratic model. If nothing is significant, we cannot fit the quadratic model here. So these values we have identified through optimization. After this, you have to do one more stage in the data. So you can see the optimal value. If you have the L value 76.40, A value minus 12.65, B value minus 77.00, you will get the pleasant value of 1.7, interesting value of 2.4, exciting or value of 1.4. These values represent the degree of feelings you are getting in your mind. Because semantic differential actually measures the emotions. Semantic differential, it measures a kind of emotional responses. And the desirability value they have given 0.768 here, but ideally it should be 1. Desirability should be 1. But since it is a psychological study, getting an ideal desirability will be a problem here. But in food technology, whenever you are doing analyzing the data, you will get the desirability value 1. Okay. So any questions here? It's a totally different area for extension, but I think the example might have been very clear to you. Even I was not knowing, I was using the response surface for 10 years. But they only when recently, when I was talking to Helen Madam, then I never thought of showing here. Then I started reading literature, then I found recently people are using response surface for psychological work. There are one more paper is also there. 2-3 papers recently I have seen. But once you do it, you can publish in international journal. That is for sure. It is not an easy technique to use. There will be a lot of things you have to see. Maybe the same example you can try in your classrooms. Maybe you can try in a museum rooms.
Partial order activities, right?
Yeah.
Then, sir, we have to next step is meant to ANOVA.
No, everything will come. Now I will show you. Otherwise, I will show you the demonstration.
Software? That's no software. We have